let's take on some previous year gate problems from the subject RAC. So the first question is, which one of the following is a CFC refrigerant? Okay, so let's check the options and reject the options, and we'll get the right answer. So if you see options A and D, you see that they are definitely inorganic compounds, because for inorganic compounds, the designation of refrigerants is actually given by R700 plus molecular weight. Okay, so R700 series is for inorganic compounds. So if you check option D, this is R700 plus 18, and 18 is the molecular weight of water. So option D is water. And what about option A? Option A is R700 plus 44, and 44 is the molecular weight of CO2. So A and D are not the CFC refrigerants because they do not contain chlorine or fluorine. Okay, let's check the other two options, that is R290 and R502. Okay, and I will tell you that the R500 series are actually used for azeotrops. Okay, so let's check R290 first. So these are three digits. Okay, R, and then it is followed by 3 digits. So that means it is a saturated organic compound. Saturated organic compound. Okay, and the designation of the saturated organic compounds is given by R M-1 N plus 1 P. And what is M and P now? The compound is given by CmHnFpClQ. Okay, so now you understand what is M and PQ. And there is one more relation for saturated organic compounds from where we can calculate these M and P and Q, is N plus P plus Q is equal to 2M plus 2 for saturated organic compounds. Okay, so let's compare R290 with this designation, with our designation. So M minus 1 is equal to 2. Okay, and N plus 1 is equal to 9 and P is equal to 0. So this gives me M is equal to 3 and N is equal to 8, whereas P is directly equal to 0. Okay, now put these values, these three values in this equation, and what you have to find? You have to find Q. So N is 8, P is 0, Q is we have to find 2M, that is 3. So this becomes 8 and this is 8, so this gets cancelled out, and Q is also 0. So P is 0, Q is 0. The compound becomes C3H8. No chlorine or no fluorine is present. That implies this is also not a CFC refrigerant. So the option remaining is R502. This is our answer. Okay, and R500 series is used for azeotrops, and roughly R502 contains, I guess it contains 49% CHClF2 and 51% C2F5Cl. Okay, so option C is our answer. Okay, the next problem is a heat pump with the refrigerant R22 is used for space heating between temperature limits of 20 degrees Celsius and 25 degrees Celsius. These are the temperature limits given. The heat required is 200 megajoule per hour. Assume specific heat of vapor at the time of discharge as 0.98 kilojoule per kilogram Kelvin. Okay, so this is specific heat of vapor. Okay, CPV I am denoting it with. Other relevant properties are given. The table is given. The enthalpy in kilojoule per kilogram, beware of the units, in kilojoule per kilogram of the refrigerant at isentropic compressor discharge is. Okay, So I have to find the enthalpy at the isentropic compressor discharge. Okay, so let's draw the TS diagram of the ideal VCRS, something like this. This is a straight vertical line, okay, because this is isentropic compression which has been given to us, and this is the isenthalpic process from 3 to 4. 1 2, this is 2 dash. Okay, so 1 to 2 is isentropic compression, and 3 to 4 is isenthalpic process. 1 to 4 is occurring in evaporator, and 2 to 3 is in condenser where heat is rejected. Okay, so the temperature limits are, let me rub this. And get your answer. So that implies when you solve it, H2 will be equal to, its value is 433.29 kilojoule per kilogram. Okay, so this is our answer. Always try to solve the question from what have been asked. Okay, like we have been asked the enthalpy, so how can I find out the enthalpy? I can find out the enthalpy by this relation, and you actually get the term which is missing, which is required to find H2. So this way you proceed with the question. Okay, the next question. The next question is, refrigerant vapor enters into the compressor of a standard vapor compression cycle at minus 10 degrees Celsius. The enthalpy is given and leaves the compressor at 50 degrees Celsius. The temperature limits are given. The enthalpy at the state points is given, are given. It leaves the condenser at 30 degrees Celsius. Okay, and the enthalpy of the state point 3 is also given. Let me draw the TS diagram. The COP of the cycle is, okay, you have to find the COP of the cycle. It's a bit difficult to draw here. Okay, one, two, 2 dash 3, this is 2 dash 3 4. Okay, COP of the cycle is equal to refrigerating effect upon the work input to the compressor. Okay, the refrigerating effect from this TS diagram is H1 minus H4, and the work input to the compressor is H2 minus H1. Okay, now we have to see what the values are. What the values of H1, H4 and H2 are. Okay, some data is given that refrigerant vapor enters into the compressor at state 1. That implies its enthalpy is equal to, H1 is equal to 402 kilojoule per kilogram, and it leaves the compressor, which is 0.2, and whose enthalpy is given as H2 is equal to 432 kilojoule per kilogram. Okay, it leaves the condenser at 0.3, and its enthalpy is H3 is equal to 237, as 3 is equal to 237 kilojoule per kilogram. Okay, so what about H4? We know that H3 is equal to H4. Why? Because this is an isenthalpic process, isenthalpic throttling. Okay, so H3 is 237, which is equal to H4. Okay, now we have H1, H4, H2, we have all the values. It was a pretty straightforward question. So this is equal to, the difference is equal to 165 upon 30. COP is 5.5. Okay, the COP of the cycle is 5.5. So this was a pretty straightforward question. Let's move on to the next question. Okay, so a refrigerator uses R134A as its refrigerant and operates on an ideal vapor compression refrigeration cycle between the pressure limits of 0.14 megapascal and 0.8 megapascal. If the mass flow rate of the refrigerant is 0.05 kilogram per second, m dot is 0.05 kilogram per second, the rate of heat rejection to the environment. Okay, the rate of heat rejection to the environment in kilowatt. So draw the TS diagram of an ideal VCRS cycle. I mean vapor compression refrigeration cycle. This is again a straight vertical line. Okay, this is dotted line. So 1, 2, this is 2 dash 3, 4. Okay, the data which has been given is I guess it's m dot 0.05 kilogram per second, and this data is given that at pressure 0.14 megapascal, enthalpy of saturated vapor is given and entropy of saturated vapor is given. Okay, so first of all, let's see the rate of heat rejection to the environment is what is the equation of this rate of heat rejection. So heat is rejected in condenser, so that implies the enthalpy change from 2 to 3 multiplied by its mass flow rate will give me the rate of heat rejection in kilowatt if I put the enthalpy change in kilojoule per kilogram. So rate of heat rejection will be m dot H2 minus H3. Okay, now all we have to see is that do we have the values of H2 and H3, and I guess from the data we will get these values. Okay, so let's find out H2 first. So H2, this value, okay, that is at pressure 0.8 megapascal, and this is happening at 0.14 megapascal. So at pressure 0.8 megapascal, enthalpy is given, but let's see what is the, I mean, the enthalpy of which state is given. So enthalpy is 272.05 kilojoule per kilogram, and entropy is also given of superheated vapor. So directly this enthalpy is H2. Okay, so H2 is 272.05 kilojoule per kilogram. Okay, and at pressure 0.14 megapascal, saturated vapors enthalpy is 236.04. So H1 becomes 236.04 kilojoule per kilogram, and I have to find H3 also. And the third data is at P is equal to 0. megapascal, the enthalpy of saturated liquid is 93.42. So that is this H3 is 93.42. Okay, so we have all the values. So rate of heat rejection Q dot R is equal to 0.05 multiplied by the enthalpy change, that is 272.05 minus 93.42 kilojoule per kilogram into kilogram per second, which will give me the answer in kilowatt. The answer will be 8.9315 kilowatt. This is QR dot. Okay, let's move on to the next question. Oh, this was a very nice question asked in GATE 2016 set 3. A very beautiful question. Do try to solve this question before seeing the solution. Okay, stop this video, solve this question, try this question first. Okay, so if you have tried this question, let's see what this question says. So in the vapor compression cycle shown in the figure, the evaporating and condensing temperatures are 260 Kelvin and 310 Kelvin. Okay, so this is the condenser temperature, that is 310 Kelvin, and this is the evaporator temperature, 260 Kelvin. Okay, and the compressor takes in liquid vapor mixture at state 1 and is isentropically compresses it to a dry saturated vapor condition state 2. Okay, so basically it is explaining this process which is given to us in the figure, the specific heat of the liquid refrigerant, that is, this is CPL, and the value is 4.8 kilojoule per kilogram Kelvin. Okay, and it may be treated as constant. Right, this assumption is also given. The enthalpy of the evaporation for the refrigerant at 310 Kelvin is enthalpy of evaporation, that is HFG, and in this case HFG is equal to H2 minus H3, and this is equal to 1054 kilojoule per kilogram at 310 Kelvin. Okay, so H2 minus H3 is given to us, that is 1054 kilojoule per kilogram, and I have to find out the difference between the enthalpies at state points 1 and 0. So I have to find out the difference between H1 and H0, that is I have to find out H1 minus H0. This I have to find out. Okay, so how can we proceed? I mean, how can we solve this question? The only equation that I see where I can solve this question is this is an isentropic process, so that implies S1 is equal to S2. So if I write the entropy at point 1 and point 2, maybe I can get to some point. Okay, so let's try and solve this question. So for finding the entropy at a state point 1, I have to actually take a reference temperature T, from which we will be calculating all the values of the state points, all the entropy values of the state points, because no data is given, no entropy value is given. So I have to actually take a reference temperature T, from which I will be calculating all the values of the entropy at the state points. Okay, so let that reference temperature be T. Okay, now let me draw this figure more clearly. This is again a vertical line. This is point 1, this is point 2, this is point 3, and this is 4. This point is 0. Okay, so let's take a reference temperature T. This is T. Let this be T. Okay. Can I find S1? Because now I have the reference temperature T. Can I find the entropy at point 1? Yes, I can find the entropy at point 1. It is actually written by H1 minus H0 by T plus CPL ln. This temperature is 260 Kelvin and this is 310 Kelvin. I'll explain how I'm writing this. 260 by T. Okay, so this part is actually HFG by T. Okay, because when we have a mixture of liquid and vapor, the entropy is actually given by this equation. So for this part, from point 1 to 0, the entropy is HFG, H1 minus H0 by T plus the entropy of this part from point 0 to T, and it is actually given by CPL ln T 260 by T. Okay, so this 1 plus 2 will give me the entropy at state 1. Similarly, at point 2, S2 now is equal to the entropy change from point 3 and T and the entropy change within the point 2 and 3. Okay, so this portion plus this portion will give me the entropy at point 2. So for this portion, that is from 2 to 3, this will be actually HFG by T, and HFG here is equal to H2 minus H3 upon T plus For the portion in the liquid region, this will be given by CPL ln T3 is equal to 310 Kelvin upon T. Okay, now S1 is equal to S2, we know this. So H1 minus H0 by T is 260 plus CPL is 4.8 ln 260 minus 4.8 ln T is equal to S2 minus S3 is given as 1054 by T, that is 310 Kelvin plus 4.8 ln 310 minus 4.8 ln T. Oh, see, this temperature is getting cancelled out. So be sure that if the data is not given in the question, that means the data which you will be assuming will actually be getting cancelled out. Okay, be sure of that. So this gets cancelled out. Now the only variable part is H1 minus H0, and rest all the other things are given to you. Take this 4.8 ln 260 in the right hand side, solve this equation, and you will get the value of H1 minus H0, which is equal to 1103.511 kilojoule per kilogram. So the key point here was to assume a reference temperature, and you have to calculate the entropy values at the state points 1 and 2. Okay, and for state point 1 the entropy will be equal to the entropy change in the liquid region plus the entropy change in the dome region. Okay, and similarly for point 2 the entropy change will be equal to the entropy change in the liquid region, that is from point 3 to this T, and in the dome region. Okay, so this was a good question. Thank you.